Derek Leon did at Google Next recently. And Jason asked us to talk about this a little bit. So we'll talk a little bit about Twitter infrastructure. We'll give an overview of our evaluation to see how we came to a conclusion to move part of our infrastructure to cloud. We'll talk a little bit of recommendations, and if we have time, questions, and maybe even answers. Maybe answers. Oops. So we set out to answer a few strategic questions. Some of them is, what is our long-term strategy on cloud versus staying in the data center? When we started this discussion a couple of years ago, it wasn't quite clear, and a lot of people had a lot of different opinions. The other obvious question was, which cloud provider to use, and we engaged with several of the large cloud providers. You can imagine, what some of the names were. And then a very big question which you had to answer is, how can we become confident in the answer that we're going to arrive? Because there were so many different people with different opinions and held it very strongly that was an important part. And then the last section was like, why and how should we evaluate this? And this was back in 2016 that we started this process. And the more technical questions we set out to answer were more around what is the feasibility and cost of large-scale adoption of cloud? So we knew that having 100 servers here or there, or maybe even 1,000 servers, that's fine, it's easy. We had that in different sub-parts of our company already on the various clouds. So the real question was, how do we do a large-scale adoption, and is that even possible? And then with that, what are the workloads that are most reasonable to move over to cloud? Other questions we wanted to answer is like, how would this change our architecture? And how do we get an actionable plan? So the evaluation process for us started quite a while ago, and this may be very different if you're coming up to a decision to either renew part of your data center or not. Then you may have a very different process where you might be forced out by a deadline. And we've talked to several companies who have done migrations, and they were sort of forced by a deadline of we need to renew a data center or not, and therefore we're going to try to not renew and then force out. We took a slightly different approach, and we had a longer horizon. So we were able to make a more patient and more rigorous decision. So we looked at our workloads, and that scanned from all of the different kind of workloads that you had, from search to ad serving to databases to key value stores. We looked at everything across the board, and with some of those workloads defined and in mind, we engaged with several of the vendors, and we asked them for a proposal to work with us to see what we could do. We then analyzed several of the large vendors and really started looking at what does it take to look on that environment? And Lohit is going to go into more detail on one of those specific evaluations. So the rough timeline, I'm not going to go through a huge amount of detail, but you can see we started in June 2016 and made a final decision in June 2018. So it took us 2 years to do the full evaluation, to get everybody on board, to get everybody comfortable with the decision. And then at some point we thought we had decided, and then we went back and got more data, more information, and more financial modeling. So quite a bit of work has gone into this. And then we built an overall cloud plan. The specific interesting part here is that we ended up building quite sophisticated financial models and projections to figure out how it would work. And we looked at a bunch of candidate architectures to see would we go on, and there were several other business considerations as well. Specifically, the financial modeling, there were lots of things that went into this. This started out with a relatively simple plan of this is the cost per core, and this is the cost per core, this is the cost per RAM, and this is the cost per RAM. But then as we started thinking more and more, well, at some point, you're going to have Moore's law, and at some point, you're going to refresh on-premise, and at some point, you're going to change things on cloud, and we're changing our networks on-premise. And so, we ended up building more and more of these factors into our models. And in fact, we ended up building 2 independent models to give us more confidence. And it was interesting that in the beginning, there were some constituents at Twitter who were convinced that, well, clearly cloud is going to be cheaper, of course, because it's cloud, so it must be cheaper. And we found actually that's not necessarily always the case. If you're operating at Twitter scale, I'm sure like some other large companies working at scale, you don't just go and buy hardware off the shelf from a commodity hardware company. You have more dedicated hardware that fits your specific use cases and needs, and you're having large enough volume that you can actually be very cost efficient. So what we found is that an immediate all-in fork and lift and shift of picking up the entire Twitter infrastructure and dropping across, that would be expensive, it would be highly distracting, and would be very, very risky. We also realized that if you pick up the entire infrastructure, one very large component of that is that for quite a while you have to be running in both data centers at the same time, or both your own environment, multiple data centers, and in the cloud environment, in case it works or doesn't work, or you have to go back. So those were very important factors that went into the cost consideration. We looked at Hadoop and said, and we'll talk about that a little bit more on the next slide, but we said there are some very specific, interesting parts that Hadoop specifically would be a possible interesting use case for cloud. And all in all, over the 2 years of period and lots of evaluations and lots of back and forth, we gained more and more confidence in our decision to invest both on-premise, on our own data centers, as well as into the cloud. So we decided to go with a dual cloud strategy that later on was dubbed by one of our team members as partly cloudy. So I'll hand over to Lohit, who will talk a little bit more about the technical stuff, and I'll come back at the end and talk some about some of the conclusions.
Thanks, you. So first, a little bit about the like a Twitter Hadoop at Twitter, like a scale. So we have about like 500K cores, 300 petabytes of logical storage. So that's about like exabyte of like physical three-way replicated HDFS storage. Our peak clusters are about 12,500 nodes each. And we ingest about like 1.4 trillion events a day. So that's about like 4 petabytes of data every day. So the scale is quite amazing. And we have different kinds of clusters, Hadoop clusters, based on the use cases. For example, we have real-time clusters which have a very high SLA. Like the uptime on those are like few years. We never bring down those clusters. These are all the clusters which are like the incoming clusters for all the events which we get. So the compute on those are like about 10%. We don't really run any production jobs on those. Very, very like high available, like some specific use cases run those on multiple data centers. And the majority of our other cluster are like our production clusters. These are the clusters which run like regularly scheduled jobs, which are well tested and which are like either hourly, daily, or weekly jobs. So the compute on that is like about 60%. And we also have like large ad hoc ad hoc clusters which support our ad hoc use cases. We also have like a lot of cold storage. The compute is not that much. It's mostly like dense storage clusters. So basically we have so this is the processing, like in terms of size of the clusters and such, right? So yeah, so the for example, cold, we rarely run any jobs on those. We do have some, but mostly it is for like storing data, right? So we have like several different challenges while managing these huge clusters across different dimensions. For example, scaling, like we have a significant year-on-year compute as well as storage growth has been happening for a few years. Hardware, we couple of years back, we specifically tuned hardware, like we went with a different kind of configuration based on the workload we did before. We have like a huge challenge around capacity planning, and we have like projects like HRaven and ATS, which really help there, because it's very hard to predict like how much we have to order ahead, right? Because especially with ad hoc use cases, and we have to move like pretty fast on all these things because use cases are always changing. Deployment is a big challenge. For example, we worked quite a bit around like rolling upgrades, upgrade domains, because these are like very large clusters. We cannot bring them down and then update and then update the software. And network. So as I explained, we have multiple clusters across multiple DCs. We always try to sync the data from one cluster to another. So network is really important for us. And definitely for disaster recovery, we maintain multiple copies. So when we looked at what are the hardware requirements to support this, right? So we definitely needed a sustained like a network bandwidth per core. We also need a sustained disk I/O per core. Mostly the use cases are large sequential reads and writes, just like for Hadoop. Mostly around throughput and not latency. So CPU and RAM, even though our utilization is very high, we can scale that. Like we can add more nodes but we need to make sure that the network and disk are not bottlenecked. And most of the time, as Milind also mentioned, like we no longer look at like individual files. For us, it's all data sets. So we have a service where people look up that data set on an hourly partition or something, and then they act upon that set of data sets, right? So when we were trying to compare what we have now and what we would need on the cloud, so these were the ranges we had. Like we had clusters anywhere like 10 node cluster to 10K node cluster. And our network ranges from like some nodes have 10 gig and some have 25 gigs. And the disks also varies 24 terabytes to 72 terabytes. CPU is like 8 cores. This is like an average across all the clusters. If you look at the network, it's actually, that is the interesting part. Like the network sustained is like 20 megabytes, but it can peak up to like 10x. So this depends on the ad hoc nature of a job, or we lose a rack and we start replicating, and we start replicating to other clusters. There's a backfill. So there are various different things which can add up. And so we have to make sure that we can account for that, right? This that is per node. Yeah. And so basically, when we said, okay, we'll start evaluating, there were really two options for us. One was to use Hadoop as a service in the cloud, um, which was the data proc, or we had an option to get our Twitter. We have like a Twitter Hadoop build, which is very close to the open source version. So get that on the cloud and use the GCS as a durable storage. But for intermediate, you have various different options, whether you use GCS or local attached SSDs or PD. They have this concept of PD on hard drive. So there were different options. So, and the test plan looked like, so this is kind of like a template. Whenever we want to evaluate like a new hardware, we have like a well-defined template, and we also have all the results with existing hardware so that it is easier to compare. So we said we'll do test TFS IO, various different things, replication, no replication, read and write, different block sizes and such. Then TerraGen and TerraSort. This will basically evaluate the entire stack, like the Hadoop stack, and pretty much like covers the base case, right? But we also said, okay, we want to make sure that our jobs, our workload can run, and we have like a good comparison. So we ran grid mix on 1K jobs and 1K, 2K, and 5K jobs, so that we can compare the difference. We also tested about various different like consistency models as to like how we would place the data, different zone, different regions, how we would recover and such. So the evaluation, as I said, we went with the data proc. So at that time, the version supported was 2.7.2, which was very close to what we were using. And we went with like 100 N1 standard 8, 8 vCores and 30 gigs. And we also tested with 200 N1 standard vCores. We did a scale testing with 1,000 of these instances. And it was like basically modeled across like our production clusters. There was no preemptible instances when we started off, and it was like very similar to, as I said, very similar to our internal configuration. So what we noted was that when we used and from the beginning we decided that okay, all the durable storage would be GCS because of various different features it will provide. So the durable storage was always cloud storage. We tested with local SSDs. That was like very performant when we ran like IO specific benchmarks, but then it was very expensive to get so many SSDs onto each of the instances. So the other options we tried was have the data in cloud storage, and then the HDFS for scratch space, like our shuffle data and the intermediate output out of these map reduce steps. So there, when we did the comparison, it was like almost like 1x of what we get internally. And then there was not much difference even if we had the HDFS via direct attached or on the cloud. So not much of a difference there. We also ran with 200 of those instances, similar results. So we were said, okay, so this combination looks good. But what we also ran like a lot of grid mix, our workload, and that overall we got like about 1x very similar results. So what the takeaway was that so even though the standard benchmarks can vary and then look different, what you really need is to make sure that you run the grid mix, your workload, and to make sure that those perform as expected. And we also discovered that it doesn't matter, like you don't need a local attached storage. We should be like even over the network. It was fine. We didn't have any issues. We also did not notice anything with the live migration. Like Google had this feature of live migration. There were some other use cases. For example, we have a key value storage team. They were also evaluating in parallel. There they used to see some few seconds delay when the live migration was going on. But for Hadoop use case, it didn't matter. Out of this, Google also, along with our team members, submitted this patch to get composite CRC checksum for HDFS. So that was useful. And the other use cases, they also saw that fsync was like once in a while, it used to take a long time. For Hadoop, it didn't matter that much. But for other key values kind of use case, it did matter and bubble up. And then Google actually fixed it pretty quickly, like within a week, they fixed it. Yeah, so you will now talk about the outcomes. After we did this evaluation, what happened next?
So after we did this this long kind of evaluation, we concluded, like I said a little bit earlier, that we disqualified the lift and shift of everything. So we decided not to pick up the entire Twitter infrastructure, move to the cloud, and drop it in there. Even though that would lead to the fastest possible migration, and it would limit the duplication of data and infrastructure running on both sides, we decided we would not do that. It would introduce a lot of tech debt after we migrate, because we would essentially pick up everything as is, move to the cloud, and then we would look at re-architecting. So that was not a very good benefit there. And there were a lot of concerns around the overall cost, the amount of risk, the number of distraction. If the entire company would be focused on moving an entire infrastructure over to a completely underlying platform, would there be a lot of lost opportunity? So we decided to not lift and shift all of Twitter into the cloud. The Hadoop use case was interesting for several reasons. First of all, it was more separable with fewer dependencies than other systems. We didn't have a super large number of low latency sub-millisecond request, back and forth requirements that other systems had. So you couldn't, for example, take your user graph and stick that in cloud and then say, oops, well, if the network connectivity is down for an hour, then, oh, well, we just don't serve users for an hour. That requirement is not as intense with the Hadoop use case. Hadoop, on Hadoop, we use an open source platform that has a fairly high level of abstraction for our users. So for our users, whether they run a Hadoop job over here or over in another cluster, it doesn't matter that much for them. So that reduces quite a bit of risk and also reduces some of the lock-in risk. As long as the use cases still remain on the level of abstraction of Hadoop, they can run on-premise as well as in cloud, and we can move back and forth. We also realized that re-architecting is achievable. So specifically, the re-architecture we're talking about here is the splitting of the storage and the compute part. So as Lohit pointed out, in the evaluation on Google environment, it didn't matter much if we had a local attached storage or a local disk or cloud storage, GCS. That was not true for the other cloud vendor that we evaluated in depth. There was actually a lot of challenges there. So we found that network is a very, very important part. It is a very important factor in this. The other advantage is when we separate the storage out, now we can start leveraging other kind of compute frameworks and other kind of offerings from the cloud provider and use that with the data. So once the data is there, we can still use the normal Hadoop use cases the way we've done before, but it becomes a little bit easier to have other things done. And we made a longer term bet that the Google platform and the Google ecosystem around tools and data processing was going to make a lot of rapid progress. So even in the 2 years' time that we have engaged with them, we saw a lot of movement forward, and we got a very good engagement at a pretty deep technical level. One of the examples is the checksums that didn't exist before, and we just asked them, what happens if we have a checksum failure between the original source and the final target? that didn't originally exist. What did exist was from the node where you upload into the GCS storage, there's checksums there because that goes over HTTP. But we found like, well, we need to have an end-to-end because we're moving 300 petabytes of data. There can be corruption along the way. So we're able to like fairly quickly turn around and make those kind of enhancements. So that gave us confidence that, that the ecosystem would evolve. So we talked a little bit about, scaling the dimensions separately, separating, the multiple clusters and having multiple frameworks run. That is a very large advantage. The other components that we want to start leveraging in cloud is primitives around projects and smaller networks. So on our infrastructure in our own data centers, it's more of a flat environment. Whereas if you go to cloud, there's more components and more parts available to separate different clusters into different environments and get better composability in that sense. And we can treat storage more as a commodity, albeit we still have to do a lot of work in sort of bridging the difference between HDFS and GCS. GCS is an object store, it's not a file system, so there's still some interesting challenges that we have to tackle there. So we call our project partly cloudy because we are going to be moving our cold clusters and our ad hoc clusters to cloud. Our production clusters stay on premise. So for the cold clusters, they're very storage intense. We hardly run any compute, so we could use something like on-the-fly data proc clusters, Hadoop as a service if needed. And the scaling goes mainly around the amount of storage. On the ad hoc side, we have much hotter clusters and much longer clusters. We're going to be running long-running clusters that we provide ourselves. One of the main reasons there is that if every user case spins up their own cluster, the average utilization of those clusters are going to be very, very low, because you're going to have to scale that cluster for either users for ad hoc don't even know how to scale at all, and they're going to just choose value X that's going to go into some sort of internal wiki, or you have to estimate it for the largest part of the site of the job. And imagine that you have a chain of map reduce jobs. Every time when you're running reducers, the rest of the cluster is going to just sit idle. But we have very spiky, we have a very spiky nature on our ad hoc cluster, so we can scale that up and down. Our production clusters, as I said, are going to remain on premise. That leverages, purpose-built hardware. We have fewer processing frameworks because these are production jobs that run stable. So, and they're not as easy to separate out. So we're going to leave those on premise and move part of our structure, hence the name partly cloudy. So the benefits of that is that we can, make use of some of the next-gen architectural components, like I said before, where we can leverage some components of security in that we have in cloud, some isolation. We can use things like live migration, where the underlying OS stays and the virtual machine just moves around that we don't have to worry about. We're part of a larger ecosystem. We can, lean on Google for some of that stuff. The other very interesting part is the argument here that our team becomes a beachhead. So in order to move a large part of infrastructure across, some team has to be the first. And sort of the stuff that you're used to in a large company, there's a lot of infrastructure, not just physical hardware, but a lot of tooling that's available. And some team has to make that happen. For example, how do we do key management? How do we do observability? How do we do deployment? How do we do source control? How do we do auditing? All of the kind of stuff that on-premise we're all used to, and we're, every company has their own flavor of these stacks of tools, but that all works within our data centers and works really well. Now we need to just, somebody needs to go make all those things work on cloud. And, by our team being the first one to do that, we sort of, lay the foundation for other teams who are going to use much smaller use cases. So let's say a Twitter front-end service wants to terminate some traffic on the Google Cloud to stay closer to the end users. They don't have to go through all of these things for a relatively limited use case. So by our team being the first one to have to go through this, we make that available for other teams to use after us. The other things that are available is, particularly for ad hoc use cases, we can very large scale up and scale down. We avoid some of the scaling limitations on HDFS. We've reached some of them by going to a federated model, but as clusters keep growing and growing, that becomes more of a challenge. Once you go to cloud, it's sort of no longer our problem. It becomes the GCS problem, and they can they can have their engineering help with that. We end up getting an offsite backup by having a data storage there. And we have a larger availability of our cold clusters. Currently, our cold clusters are on a separate set of machines in a separate cluster that are very dense and are rarely used. But by sort of like all putting together into one larger pool of GCS, we don't really have to distinguish anymore. And on the right hand side, you see a bunch of other items that we can have. Specifically, we can start using services such as BigQuery. We can start using Spanner, cloud machine learning, and other kind of components and things that cloud offers. So some of the things that we found, even on cloud, there are limits. So when people say serverless, my standard reply back is like, calling cloud serverless is like calling takeout kitchenless. There's still a kitchen there, it's just not your kitchen, right? So there's still servers, they're just not your servers. So there's some limits. So if you just show up and you ask for more than 10,000 CPUs or 100,000 CPU differences between one and the other, you need to still, talk to cloud. So even on cloud, there are limits around what's going on. We've also found that sort of the automatically scaling up and down clusters, that is sort of like the promised land of cloud. Hadoop is not quite ready for that, right? Since we have state that's involved and computation that's going on, scaling up is very easy. So when your cluster is not big enough, you can rapidly ramp up. But to certainly cut that cluster down again, you're going to lose the state that you had in between. So that shrinking down would still be in the order of magnitude of days rather than spike up and then go down in minutes. So there's limited advantages there. And there's also some limits around how big each individual cluster can be. Even Hadoop as a service, but even some of the network stuff, there's going to be challenges when you want to make one of these 10,000 node clusters. So we need to still look at some limited size of smaller clusters. So here's a little bit about what we have done, what we are done, and what we're still working on. So we've laid some foundational work. And with we, I mean the larger Twitter organization. The Hadoop team didn't necessarily specifically lay cables and do networking. But we have a fairly decent interconnect with Google data centers, 800 gigabits per second. We've created a specific dedicated copy cluster. So we decided to have a dedicated copy cluster that has internet access through these specific internet links to GCS storage, so that not all Hadoop clusters will be copying out. We're using this copy cluster to funnel through. We're already copying petabytes of data to cloud, so that's already running. And we had some early use cases around some data sets where we end up using Presto, rapidly scale it out to 100,000 cores and run through a 15 petabyte data set and then shrink down the cluster again. So there have been some specific use cases that are already up and running and already leveraging this infrastructure. On the other hand, we're still in progress of finalizing our bucket and our user creation and the access control primitives in the design. I think we're fairly confident that the approach we're working with is going to work, but we'll see until it's actually fully in production. We're working on productionizing replication tooling that makes sure that we can copy from multiple data centers. So some specific stuff that's happening there is that in the past we would copy from one cluster to one other cluster, but now we're going to be copying from multiple clusters to a target location, and specifically combining those data sets in one GCS location has some interesting properties and complications. There have been already a bunch of enhancements to the GCS connector. Lohit talked about the checksumming, but there's a bunch of other open source contributions being put back around seek optimizations, and a lot of those kind of enhancements have already gone in. And we're currently in negotiation and working on tooling around how do we manage retention? Can GCS do some retention automatically for us? How would that work? And specifically also around atomicity. That there are some differences between GCS and AWS with consistency. So individual objects are strongly consistent, and individual operations are strongly consistent. So that's relatively easy on Google, but it's still on individual files. So if you talk about an entire data set in a directory, there's still interesting things that can happen. Think about an entire tree of the year, month, day, and you move an entire year out of the way. That's not one atomic operation like you have, because there's no inode like you have in HDFS. So what we found is, don't just look at individual prices. Actually run your application level benchmarking, such as grid mix. Capture a workload from your own data centers, from your own clusters, and run that to compare. And when you do that comparison, we found that the network is hugely important. That was one of the major factors why we decided for one vendor over another. And evaluate whether an entire lift and shift is the best. We've talked to several other companies, and they ended up just going with the lift and shift first, move as fast as we can, and then ask questions later. Evaluate if that's the right thing for you, or if you want to sort of split things out as you go along, and sort of re-architect as you go in. So for us, the separating compute and storage is a real thing that's really going to make a big difference, and that's specifically because of the network and the way the storage works in an environment. The cloud adoption is very complex, so this ends up being more of a culture shift than just a very large, complex project. We're still early in the process, so we're prototyping. Some use cases are running, so we have lots more things to share as we're going on. Anybody have any questions about what we have talked about so far? Two questions, one for Lohit.
Assume PD is like EBS. Is PD, you mentioned the word PD, is that like EBS on Amazon?
Yeah.
Okay. So even...
So, yeah, but it's
PD
much,
is direct storage?
yeah, it's much faster than EBS.
Okay, but it is not local disk.
No. No. Okay. So in Google, there is only a local SSDs. They don't have a hard disk anymore. The only option is SSDs, but it's very expensive. Right. So PD is like a persistent disk, but it's network attached. So, but the consistency,
it's close
yeah,
network.
Yeah, but it's very consistent.
So we got a similar thing when we were working with Google, that you should use the PD for your intermediate data, like you mentioned. And then you kind of concluded that local storage doesn't matter or something. So you were basically saying that you are still using PD. And with that, you found you're using it for temp storage and intermediate storage, right? And then you found there was no performance difference, even though the object store may be slow. This covered the most of it. Okay, so
Yes, that is right.
Now, from your cost point
on Google side.
On Google side, I got that. So, on a cost point of view, are you finding that storage, because storage is 724, right? And then you have compute, which can actually be, you can take advantage of spot pricing, shut down when you're not using, and optimize. From your pricing comparison, were you finding that storage was actually comparable in cost with your online, with your on-prem clusters, given that you are pretty good at buying at reduced, very heavily discounted prices?
So, yes, storage is always on. No, we're not at the moment looking at shutting down compute when we're not using it. So we're looking at having relatively large shared clusters that are on all the time, and only once in a while, on occasion, spiking up or running on an ad hoc cluster somewhere else. So by and large, we're going to still have large shared clusters that stay up and running, and we use Yarn to bin pack all those compute load cases into that cluster itself. So we're not shutting down clusters and spinning them all the way down. And
there you're finding the cost to be comparable or cheaper on the cloud than on-prem
we found that storage is, or the overall cost is comparable for both storage and compute, yet we still have an interest in doing something on cloud.
Okay.
And this is a use case where we can make use of that.
Okay, thanks.
Do you have multiple PDs per VM, or is it only one? Because you mentioned it's a multi-tenant cluster, right?
The question is if we have multiple PDs. From what PD is concerned, it doesn't really matter whether it ends up being one or two. It's just storage, and you can scale the storage to larger and smaller numbers. So at the end,
but you have multiple jobs from different users all running on that same VM.
They're all run on the same VM, just like they run on current workers, and they all share PD and they all write to PD. So shuffle and all that kind of stuff all write to.
So you don't see any, hit because they're all racing on a single disk or something.
We've been with the right mix of cores and PD that works, and that's one of the advantages that we found, is that we can scale them independently. So we can have some clusters with more memory per core and some clusters with smaller memory per core and some more. So we're still relatively flexible in shifting that. When we are designing our own hardware, we have to very, very carefully look at that, because you buy that hardware and you sort of lock in that ratio of network and disk and core and IOPS and those kind of things. Whereas on the cloud, we're a little bit more flexible in shifting that.
So you mentioned in two questions. One, in one of the slides, you mentioned something about a copy cluster. What forced you down a path of a copy cluster?
The primary reason is that we don't want to have every single Hadoop cluster be able to attach to a public IP address, which is GCS is a public endpoint at the end. And we don't want to have all the data excreted. We want to be able to have, first of all, we want to be able to like easily start and stop and throttle what goes out.
Okay.
So by having a dedicated copy cluster and doing DCP that pulls from the original source clusters and pushes it out to GCS, as well as a place that pulls it in and then pushes it out again, it gives you the throttle point where you can relatively easily, using yarn and memory and a number of containers, scale up and down your compute. And by having different containers and different priorities, you can have different workloads that can balance. If you let anybody copy anything on a 10,000 node cluster and people spin up 80,000 containers to start copying to cloud, network gets, just bombs out, and you would have to go through proxies. We didn't want that. So those are specific nodes that have dedicated interconnects. They're specifically configured to talk to cloud internet through our interconnects. And those are the clusters where we can keep more control over who's doing what. We can have more logging.
Perfect.
Not everybody's going to run their stuff there.
Okay. We kind of thought that was what you were doing. Second question was, you mentioned one of your kind of trial use cases where you spun up a Presto cluster. Can you elaborate on what that use case was in a little bit more detail?
Okay, so I don't know whether we can talk about specific use case, like what, but the idea was there is like 15 petabytes of data, which is like for a year or something. And the use case is once in a while, you get this request to scan that entire data set. What used to happen was internally it used to be very difficult to provision like a Presto for that. And here all you have to do is the data is sitting there. You just spin up the cluster on demand, like the Presto cluster, and then scan and then shut it down.
The data is where? Sorry?
So the data is in GCS.
So the data was already in GCS. You're just spinning up the compute.
Yeah. So imagine some law that came into effect not too long ago, where there are certain requirements that sometimes on very short notice, you have to do a very large computation and deliver that result.
I can't imagine.
No, exactly. So I'm not mentioning any names.
Quick question on the GCS connector. We had kind of been prodding Google to donate that to the Apache Hadoop. I know we asked them to do the contract test for the file system, and they've done that, and they found some bugs and fixed them. But have you heard any news on them donating the connector code into Hadoop Common proper?
We have not heard news yet, and we're not yet pushing them on that. So at the moment, our major push is to make sure that all the contributions are open, they're contributed, and things are working, and we're enhancing. And then that could be some of the things we can help potentially.
Yeah, I think it could help
encourage
improve the quality a bit if it was integrated.
Yeah.
Thanks.
So you mentioned that you are still running the shared cluster in Google Cloud. So can you elaborate the rationale behind that? Because typically people set up different cluster for different jobs. Like they don't try to run a shared cluster. So what is your rationale behind that decision?
Right. So that's sort of the standard answer you get from people. Why don't you just spin up one cluster and then run your job and then shut the cluster down? And on the one hand, well, there's two big problems with that. The first big problem with that is now you're running 50,000 clusters in a day. So now you need to find which of the 50,000 clusters did your stuff run on. So with auditability is not fantastically easy. ATS can potentially help with that and solve that, but that's one interesting challenge with that. And then people's like, well, when the cluster's down, how do I click on the UI? How can I find what's going on? And like, well, you can look at the logs. Well, great. Okay, so we're going from an already challenging UI on Yarn history server and AM and that kind of stuff, where you drill in to see what happened and what's going on, to here you can SCP in and you can look at the log by yourself. Congratulations. Well, that's not a fantastic experience for users. ATS can potentially solve that. The other challenge is that if you spin up a cluster per job, how big are you going to make your cluster? Right? So it's not like one task that runs evenly all the way across the board. It's not like a web serving, but it maybe slowly grows and shrinks with the traffic. It's a DAG of jobs that runs that sometimes is narrower, sometimes wider. If you make your cluster too small, it will be very efficiently used, but it's going to take forever for your cluster for your query to run, for your job to run. If you make it wide enough for the widest part to fit in, then imagine that all the other parts in the DAG where you're not running the full width, the cluster sitting around doing nothing. right? So when you imagine 50,000 mappers, one reducer, 50,000 mappers, one reducer, maybe some an extreme case, but when that one reducer is running, 50,000 machines are sitting there doing nothing. But in the widest case, 50,000 machines can go, finish all mappers in one shot. So that's one challenge. When you have one job per cluster, there's a huge amount of overhead, and the overall utilization is going to be terrible. If you're running longer-lived clusters, you're better. If a cluster can dynamically grow and shrink, then that would be better, but there's challenges because you have spill. So now again, imagine you have 50,000 mappers run. You now want to run one reducer, you shrink the cluster down to one. Well, where did that spill go? Well, that's all gone. Oh, well, oops, we'll rerun it. When you rerun it, well, now that you just wasted what you just gained. And a similar story happens with Spark. Something similar will happen there. So
All right,
those are
cool.
the two main reasons.
Thank you.